Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 8, Lesson 2, the trigonometric ratios. All right, so our entire unit is on what's called right triangle trigonometry, and today we're going to really get into it. So let's take a look. Now, one thing you are definitely going to want for today's lesson is your graphing calculator, okay? Make sure to have that because a lot of what we're going to do today will be calculator work, and we're really going to need that calculator pretty much every day for the rest of this unit. So let's talk about ratios of relatively positioned sides. We saw in the last lesson that the ratios of relatively positioned sides within similar triangles are equal. When this is applied exclusively to right triangles, however, these ratios are known as the trigonometric ratios. So let's take a look at exercise number 1. Two right triangles are shown below, each with an acute angle that measures 35 degrees. Excellent. All right, so again, and these are, by the way, these are true 35-degree angles here. All right, I made sure that in the diagrams, these are both 35-degree angles. Obviously, those are both 90-degree angles. Let's take a look at letter A. Uh-oh, come on. There we go. Letter A. Measure all sides of each triangle to the nearest millimeter and place in the table below. Then calculate the ratios in the table to the nearest hundredth. Okay, so let's just be very clear. I want you to take your ruler out, and I want you to measure the length of BC, AB and AC, EF, DE, and DF, all right? Once you have those to the nearest millimeter, do the best job you can, all right? Then do BC divided by AC on your calculator. You're gonna get some decimal, round that to the nearest hundredth. AB divided by AC, you're gonna get some decimal, round that to the nearest hundredth, etc. All right, so take a few minutes. This is going to take some time, all right? And then we will go through the results. Pause the video now. All right, great. Well, I've kind of pre-done this because I didn't want to take up the 5 or 10 minutes it would take for us. So the first things first, right, for me, I got the length of AB was 33, the length of BC 23, and the length of AC 40. I got the length of DE is 50, the length of FE is 35, and the length of FD or DF is 60. All right. Now again, if you were a little bit different than me, maybe you had a 32 here, a 21 here, a 39, etc., that's fine. Depending on how much your worksheet has been dilated, right, increased or decreased in size, your values might be a little bit different. Now, once I put those into my table, right, then I get the following, right? The 23, 33, 40, the 35, 50, and the 60, those were just those measurements. But when I do 23 divided by 40, I get 0.58. And when I do 35 divided by 60, I get 0.58. When I do 33 divided by 40, I get 0.83. And when I do 50 divided by 60, I get 0.83. And finally, when I do that last ratio, I get 0.70 and 0.70. And again, your values here could be a little bit different based on what your measurements were, but they should be very close, right? This should probably be somewhere between 0.56 and 0.60, so if you're plus or minus by 0.02, you're probably fine. Now let's take a look at letter B. In any given column, the ratios you calculated in the above table should be equal for the two triangles, or at least close based on the measurement error. Why should they be equal? Explain. All right, so in other words, why should we get the same two numbers here, the same two numbers here, and the same two numbers here? Pause the video now and consider these two triangles. All right, well, keep in mind, this triangle has a 35-degree angle. This triangle's got a 35-degree angle. This triangle's got a 90-degree angle. This triangle has a 90-degree angle. Therefore, these two triangles must be similar based on the angle-angle theorem of similarity. So let's say we just take a look at BC divided by AC, right? BC is that length, right? AC is that length. Right? And then we look at EF divided by DF, right? These two ratios represent ratios of relatively positioned sides in two similar triangles, right? And therefore, they should be equal, all right? So first, The two triangles are similar by angle. The ratios will be equal because they are relatively positioned. All right. Now the cool thing though is that that means if I have any right triangle that's got a 35-degree angle, all right, then these three ratios would have to be the same no matter what the side lengths are. So let's play around with that in exercise number 2. A third right triangle with an acute angle equal to 35 degrees is shown below. Using your answers from the table in A, find the length of ST and RT to the nearest tenth, right? So again, this triangle and the two that we had up above have to be similar because they've got a 35-degree angle and a 90-degree angle, all right? And let's talk about ST, right? So one thing that we could say, right, is we could say that ST divided by RS, okay, and remember that's the vertical leg divided by the horizontal leg. Well, what would that have to be equal to? Well, which one of these were vertical leg divided by horizontal leg? Well, that would be BC, all right, divided by AB, right? So BC divided by AB, or, let me get this so that we can see it all in there, or EF divided by DE, right? It's this final column. That's what this ratio would have to be equal to, right? This has to be equal to 0.7. It has to, because that's the same relatively positioned sides as in the table above. But now, because I know RS, I can say ST divided by 18 is equal to 0.7. And now I can just multiply by 18 on both sides, and ST would be equal to 0.7 times 18, and that's going to be 12.6. All right, great. Now, I also want to figure out the length of RT. Now for that, maybe I want to think about the ratio of RS divided by RT. So RS divided by RT, well, what ratio will that be equal to? All right, now remember here we've got this side, this leg that's adjacent to the 35-degree angle divided by the hypotenuse. All right, so in terms of these, right, that would have to be this divided by this. I want AB divided by AC. Right? And that's that 0.83 ratio. Again, the same as DE divided by DF, right? 0.83. Whoop. So this is 0.83. A little more work here because now I have 18 divided by RT is equal to 0.83. All right, here I'll have to kind of cross multiply. And I'll get 0.83 times RT is equal to 18, and now divide by 0.83, and that will give me RT is 18 divided by 0.83, and that is 21.7 to the nearest tenth. And we could do that with any right triangle where we knew one of the three sides, wouldn't matter which, if we knew that one of the acute angles was 35 degrees. So now this brings us to the entire thrust of this particular unit in geometry, the trigonometric ratios. Because all right triangles that share an acute angle are similar. Now that's extremely important, right? If they share an acute angle and it's a right triangle, they have to be similar because they'll have two angles that are equal, right? The ratios of relatively positioned sides in a given right triangle don't depend on its size. They only depend on its acute angles. These ratios are known as the trigonometric ratios or just trig ratios, all right? Now there are a total of 6 trigonometric ratios, 6 of them. In this course, you're only going to learn 3 of them. So let's take a look at the 3 basic trigonometric ratios. Number 1, the sine ratio, abbreviated as SIN. We still call it sine, we don't call it sin, all right? The sine of angle A, right, is the leg opposite of angle A divided by the hypotenuse. In our particular diagram, that would be BC divided by AC. We have the cosine ratio, abbreviated as COS. Some people will say cos A. Most of the time, you just want to say the cosine of A is equal to the leg adjacent to A divided by the hypotenuse, which is AB divided by AC in our diagram. And finally, the tangent ratio, abbreviated as tan. The tangent of A is the leg opposite of A divided by the leg adjacent to A. Again, in our diagram, that would be side BC divided by side AB. All right, so again, all these things are those ratios that we looked at in exercise number 1, okay? Now, we're gonna get a little calculator work in right away. Let's take a look at exercise number 3. Use your calculator to find each of the following. Make sure your calculator is in degree mode. I'll explain that in a moment. Round your values to the nearest hundredth. How do these compare to the ratios you found in exercise 1A? All right, so first things first, right? Trigonometry, let me just erase this. Trigonometry is all about angles. And the weird thing is, up to this point in time, you have only ever measured angles in terms of degrees, but there are different ways to measure angles. You can also measure angles in what are called radians, and there's even a third way of measuring angles, what are called gradients. The 2 most common ways are degrees and radians, and in Algebra 2, you will learn all about radian measures of angles. But for us, it's degrees and degrees only. Now I'm gonna bust out of my presentation software just for a moment because I wanna be able to make this a little bit bigger. I want you to be able to see this. Now, if I'm in my normal calculator, right, then what I'll see up in this little right-hand portion is I'll either see the DEG, that stands for degree, that's what I want, or I will see RAD, that stands for radian. Now, of course, I'm using the TI Inspire calculator. If you're using a different calculator, you're gonna find this in a different spot. I can flip back and forth between radians and degrees by simply bringing my mouse over and literally clicking on that word. That's one way to do it. Another way to do it is to actually hit the Document button, go to Settings and Status, that's option 7. All right, go into Document Settings, that's option 2, and they have something here that says Angle, and notice it's in degree. If I click on that, I have a choice between radian, degree, and gradient, but again, I want degree, okay? That's where I want it to be, because otherwise my calculator doesn't know. It doesn't know whether I'm talking about degrees or radians or whatnot. I have to have that, right? So I want to know, and we're going to go back into our measurement for a second. I want to know what the sine of, let me see if I can make this a little bit bigger. I can't for some reason. How about handheld and side screen? No, still doesn't work. Anyway, keypad and side screen, right? I want to know what the sine of 35 degrees is, what that ratio is equal to. There's a button right beside the equal button, very small right now, so there's no way you can see it here, called the trig button. And if I click on the trig button, my calculator is going to go nuts, which makes me very, very worried. Nope, there it is. Okay, I can actually choose sine, just ignore all of that. All right, and I can type in 35 degrees, hopefully. It's not going to do it. There we go. And I can type in 35 and hit enter, and it will give me the value of the sine ratio for 35 degrees, which is 0.5735, etc. All right, or rounded to the nearest hundredth, 0.57. let's now get out of here. I'm going to go back into handheld only and always in front. And I'm going to go back to my full screen. Wow, that took a lot just to get there. Okay, and sine of 35 degrees is equal to 0.57. Now, in terms of my table, which we had back on the front side of the sheet, this was my sine ratio. And it's pretty close, 0.58 compared to 0.57. The only reason that these aren't identical to this was due to measurement error. All right? What I'd like you to do now is just on your calculator, nothing more than this, type in cosine 35, hit enter, and round that answer to the nearest hundredth, and then tangent 35, hit enter, and round that to the nearest hundredth. All right, well, let's hope our calculator doesn't go nuts here. I don't have a lot of faith. Oh, of course, now it's not going to do anything weird. Cosine of 35. All right, that's equal to 0.82. And again, very close to what we had before, 0.83. And finally, trig. Go over and choose my tangent, 35. Enter. And that one is right on the money, 0.70. Okay, right? So, very, very close to what we had in the calculator, or what we had in that table when we did the measurement. Again, what's cool is that these ratios only depend on where the sides are compared to the angle that you're asking for the ratio for. So sine of 35 degrees will always be the length of the opposite side divided by the hypotenuse, but that will always be the same in every right triangle that has a 35-degree angle. That ratio will always be 0.57, roughly, right? Those values are stored in your calculator. Same thing for cosine of 35, same thing for tangent of 35, okay? Now, we are going to work extensively with the calculator in trigonometry in future lessons. But first, we need to just get good at identifying the trigonometric ratios for any given acute angle of a right triangle. Students often learn the mnemonic SOHCAHTOA to help them remember which is which. In other words, the sine of an angle is the opposite side over the hypotenuse. The cosine of an angle is the adjacent side over the hypotenuse. And the tangent of an angle is the opposite side over the adjacent side. Okay, so don't worry at all about your calculator right now. We just need to be able to state the values of the ratios if we're given a right triangle. So for instance, in exercise number 4, for right triangle RST shown below, state the value of each of the following, leave as fractions. All right, so sine of angle R, right? Sine is the side opposite, or the leg opposite of the angle divided by the hypotenuse. So I always tell students it's all about the angle, right? For angle R, the opposite side is 5, and the hypotenuse is 13, so the sine of angle R is 5/13. That's its ratio, okay? Let me erase that. On the other hand, the cosine of angle R will be the side adjacent. Maybe I'll write it down like this. The side adjacent divided by the hypotenuse. So the leg that's adjacent is going to be 12, and the hypotenuse is going to be 13. So the cosine of angle R is 12/13. And finally, the tangent ratio for any given angle is the leg opposite divided by the leg adjacent, opposite divided by adjacent, and that is going to be 5/12. So let me do this. This is opposite divided by hypotenuse, right? SOHCAHTOA. Sine is opposite divided by hypotenuse, cosine is adjacent divided by hypotenuse, and tangent is opposite divided by adjacent. And when I say opposite and adjacent, I'm always talking about the legs of the right triangle, not the hypotenuse. Now, we can find these three ratios for either of the two acute angles. We just did it for angle R, what I'd like you to do now is pause the video and see if you can do it for angle T. Take a moment to do that. All right, let's do it. So the sine of angle T is the side opposite of angle T divided by the hypotenuse. Opposite of angle T is going to be 12. The hypotenuse is 13. So the sine of angle T is 12/13. Whoops, whoa, I just wanted to erase you, arrow, not move you. Cosine of angle T, that's going to be the adjacent divided by the hypotenuse. Okay, adjacent to angle T is 5. Hypotenuse is 13. So 5/13. And finally, the tangent of angle T is going to be the leg opposite divided by the leg adjacent. The leg opposite of angle T is 12. The leg adjacent to angle T is 5. So the tangent of angle T is 12/5. All right, cool. Easy enough. I love it when these kind of problems come up on the state exam, when you're just given a right triangle and you're asked, what is the sine of angle A? Oh, what is the side opposite of angle A? What is the hypotenuse? Do the division. There you've got your ratio. Okay? Let's take a look at exercise number 5. Given any right triangle, answer the following questions. Letter A. What is the sum of the measures of the two acute angles? What type of angle pair are they? All right. So any right triangle, this is true of including the one that we just looked at, see if you can answer letter A. Well, think about this for a minute. This is actually very, very important, right? When I've got a right triangle, okay, you've got the 190-degree angle, and of course all three angles have to add up to 180, so that means that the two acute angles must add up to 90. They must add up to 90. So letter A, the sum must equal to 90 degrees, and therefore the two angles are complementary. All right, the two acute angles in a right triangle are always complementary angles. They always add up to 90. Now, letter B. What seems to be true about the sine and cosine of the two acute angles? All right. Let's go back up to here, right? I don't care about the tangent right now. I just want to look at these, right? Well, let me circle the sine and the cosine, right? So here I've got, right, the sine of r is 5/13, the cosine of r is 12/13. Here the sine of t is 12/13, and the cosine of t is 5/13. What do you notice about those values? Well, what I notice is that the sine of one of them is the cosine of the other, and the cosine of one is the sine of the other. So you might say, a little different ways, is that the sine of one is equal to the cosine of the other, and vice versa, right? It's literally like they switch. Now, that should be fairly obvious, letter C. Why does B make sense given how the trigonometric ratios are defined? Well, again, let's just take a look at this one particular triangle, right? In R, right, its opposite side is 5 and its adjacent side is 12. In T, right, those two roles reverse. So the opposite and the adjacent sides reverse. When it comes to the two acute angles, the hypotenuse just stays the same. So for R, right, its sine is 5/13, but for T, that 5 now isn't the opposite side, it's the adjacent, so its cosine is 5/13. So the opposite and adjacent sides switch positions for the two acute angles. And that will always be true. So when I have two angles that add up to 90 degrees, any two angles that add up to 90 degrees, the sine of one angle will be the cosine of its complement, and likewise the cosine of one angle will be the sine of its complementary angle. And that is something that you're supposed to know and should make sense just based on how we define these ratios. All right, let's wrap this up. Now we have just begun, we've just scratched the surface of the trigonometric ratios. So if you're still a bit confused right now, it's understandable and it's probably even a good thing, right? We're going to be looking at these ratios throughout the rest of this unit, right? And we're going to get very used to sine, cosine, and tangent and how they're defined in terms of opposite, adjacent, and hypotenuse of right triangles. The most important thing to come away from today with is the fact that every right triangle that shares an acute angle with another right triangle must be similar to it. And therefore, the ratios of relatively positioned sides will always be equal. The great thing is our calculators, right, have those ratios stored within them, which we saw for that 35-degree angle, right? Somebody a long time ago went out and they took a right triangle with a 35-degree angle and really accurately measured the sides and came up with those ratios and then stored them in your calculator. And they did it for a 35-degree angle and a 22-degree angle and a 73-degree angle, etc. All right? And we can then use those ratios and that knowledge to help us solve a whole variety of problems in math that will be not just in math, but engineering and physics and all sorts of different areas. All right, for right now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.